Hello, Matthew. Are you ready to get started? All right. Well, you and I will just jump in here and we will see what we can get covered. All right. Okay, so we are going to just talk about some different terms and some different concepts that probably you've been seeing all along. You may just not have put that thought to them. So, all right, here we go, jumping in. Okay, so discovering classes. So way back at the beginning, week 4, give or take, week 3, week 4, we talked about two terms, right? We talked about encapsulation, which is the hiding of implementation details, and we also talked about abstraction. And the abstraction is keeping things to a single concept or a single entity. So rather than defining a student class that had a student class and had courses and had grades and had financial aid and all this stuff all in one class, making it a huge, enormous, giant mess kind of a thing. We keep it to a single entity or concept. So we just do just like the student demographic, and then we just do just the course and just the grades and just the financial aid. So we keep everything to a single concept, and that is abstraction. Okay. So when we're trying to determine what classes we have, so let's say you're given a problem description and you're asked to create a program, for instance, like our golf program, you're going to think about nouns, like what are nouns? Those are going to most likely be your classes. So if we were thinking of our golf and we were like, okay, a scorecard is a physical thing, it's a noun. A player is a physical thing, it's a noun. You know, the golf course itself is a physical thing, it's a noun. So all of these would be classes, but computing the score, that's not a noun, that's an action. So methods, you want to think action or you want to think verb, where a class, you're going to think of a noun. Okay, so computing the score, that's an action. Taking a stroke, that's an action. Computing an average, again, it's an action. So when you're trying to determine if something should be a class by itself or if it should be a method within a class, just try to think of noun versus verb. Okay? All right, so thinking we have this home business and we want a system that allows us to keep track of customers, product inventory, and sales. So if you were looking at this problem description right here, what would be your classes? So in other words, like what are our nouns? Customer, definitely a noun. Inventory, yeah, product or an inventory would also be a noun. And then, yeah, I mean, sales, if you're selling, you're going to think of that as a verb, but an actual sale would be a transaction that took place. So that too would be a noun. So all of those would be classes that could be created. Now they might be intertwined, right? You might, because you'll need to know what customer was involved in the sale and what product it was that was sold. So you might intertwine them a little bit, but those would each be individual classes. So excellent. Okay, now we have a library here, and we're going to have a catalog of all of our books, DVDs, CDs, etc. We need to know our customers, what items have been checked in and checked out, and by whom. So if we're looking at this, again, what would be our classes for this particular scenario? Yes. But I mean, we would have, yeah, the library we would need to abstract things from that. So we would definitely need to pull out our entities. So books, DVDs, so those could be individual items depending upon how we wanted to do it, or we could just call them an item that needs to be rented, and then each item has a type associated with it. Customer would definitely be another noun that we would identify here, or class, and then probably a transaction where they're checking out or bringing back in. So that would also be another class that we would have. So you can kind of think you're just looking at like what are nouns, because those are going to be classes, and then thinking in terms of verbs are going to be the actual methods. So the transaction would be the noun because that's an actual transaction, but the physical checking in and checking out that would be associated with a transaction, that would be a method because that's a verb, an action that's taken. Okay, so cohesion is a term that comes into play here, and this describes your abstraction, how closely all the features are related to a single concept by that class. So obviously we want high cohesion. We want things to be really related to that single concept, and if things are getting murky, then we need to ask ourselves, maybe it's time to create a second class so that we can have high cohesion. All right, so in the when we're considering the customer class and we're thinking about instance variables, so what information would we need to know about this customer? Doesn't matter if it's a library customer or if it's our home business customer. Name, definitely. Yep. Okay, phone number. We also might want to know address for the customer, right? Cash or credit, maybe a discount if our customer gets a discount depending upon what they are. So these are things we might want to know, but then we might ask ourselves, can any of these instance variables be abstracted? And is there any benefit to abstracting them as well? So we might pull an address out, like a customer might have an address object inside of it where the address could be its own class, because an address could apply to a customer, it could apply to a supplier, it could apply to employees, right? So an address would apply in all of those situations, and in all of those situations the address is going to consist of the same things, right? It's going to have a street address, might have 1, 2, or 3 lines for the street address. It's going to have a city, it's going to have a state, it's going to have a zip. You might include a country or something in there, but we could definitely pull the address out and place that into its own class. So we could abstract it out and keep things more to their single concept. Okay. Coupling, on the other hand, is dependency, so where one class depends upon another. And we've been seeing that with Lab 3 and Lab 4, where the player class depends upon the scorecard class, and the scorecard and the whole, I think, and the scorecard class depends upon the course and the whole, right? It's where one class depends upon another. So the customer class would depend upon the address class if we extract out or abstract the address out of the customer. So what we want to try to do is minimize coupling or dependency, so low coupling or high cohesion. And it sounds kind of confusing because we're definitely using coupling, but I think coupling for coupling's sake, like you only want to do what's necessary as far as coupling is concerned. We don't want to just randomly be including things in there that is not necessary. Okay, so that's our terms, you know, a refresher of abstraction. Cohesion is basically abstraction, keeping things to a single concept, and coupling is dependency upon other classes. And we talked about how to identify what classes are needed versus methods by looking at nouns in the problem description versus looking at verbs. Okay. Methods, on the other hand, we're just going to revisit these really quickly. We talked about mutator method, which changes the state of the object, and the state are the instance variables. So basically, a mutator method modifies the value of one or more instance variable in the object. An accessor method, on the other hand, does not change the state of the object, so an accessor will not change the values of any of the instance variables. Now there are circumstances where there's an immutable class, which means there are no mutator methods. The value of that object is never changed. The state of the object, the instance variables are never ever modified. What's their set, that's all they are. And we've been dealing with one of these all along, and that was the string class. Because remember, we can call the to upper, we can call the to lower, we can call a subscreen, we can call replace, we can do all that, but the original value never changes. It always returns that modified value back to you, but the value of the instance variable, the data in the object, always stays constant. So a string class is immutable. Okay, now we can have side effects on a method. So we've got our mutator methods and our accessor methods. So there can be a side effect from a method, and a side effect is any kind of modification that's visible outside of the method or observable after the method executes. So for example, in a mutator method, what's observable is that an instance variable has now been changed, and we can observe that by calling a get method to retrieve the value and recognizing that what it was before is not the same as what it is after calling the method. Now, as far as side effects go, we've actually been dealing with those all along, right, in our JUnit, our test cases, our unit tests with the assert equals, where we've been comparing the value we're expecting against the value that we get. So we've been building all of our tests based upon side effects. But there's both good and bad. Or maybe they're not both good and good, not necessarily, but there's both intended, where like in a mutator method, we intend the value to change. So there's intended, and then there's some unintended side effects as well, things that should not happen. All right, so here's a side effect. We have public void reset dog D. So this reset is setting it back to the default values. Okay, so we'll set d.name equal to unknown, d.breed equal to unknown, and the age equal to 0. Okay, so it just resets everything back to default values. So the side effect here is that this dog object has been modified, and we can observe that outside of the method. So once the method is finished, we could call the getName method and see that its values changed. We could call the getBreed and see that it's changed, and the getAge and see that that's changed as well. So this is an intended side effect. Okay, it's changed the state of this dog object by modifying its instance variables, and it's observable. We can observe it by calling get methods. Okay. This method, on the other hand, this is a copy dog method, so it's going to create an exact copy of this dog D and return it as a dog object. So it takes in this dog here, it creates a brand new dog object, and then it takes in the values from here and uses it to create an exact copy, just a different location in memory, and it returns this dog object. This one does not have a side effect, okay, because we're not changing the original object. This dog D is not being changed. We're just using its values to create a brand new dog object. So we're creating this brand new dog object and removing it and returning it. We're creating a brand new dog object, returning it, but the original object is not being modified. So if we were to call the get methods on this original dog D, we would find that the instance variables all contain the same values that they did prior to calling this method. So there's no side effect in this particular method. All right, you guys following that, where this one here has a side effect because we have actually changed the state, and then here no side effect. Okay. This one also has a side effect. We're doing a set name, so we're setting the name to a new value. So this one has a side effect. It's intended. We can call the getName method to compare it to what it was before, and we can definitely see it. This one has no side effect because we're not modifying. We're retrieving a value, so we're not modifying it, so no side effect here. And again, this one is computing interest, but it's not changing the value. It has a local variable that it's using, but it's not changing anything. So it's immutable. Okay, so we're computing the interest. We're using some explicit parameters and maybe even using some instance variables, but we're not changing an instance variable. Okay. Now this one, on the other hand, has an unintended side effect. Okay, so before they were intended because we wanted to change the value of our instance variables. And this one, we're printing out this the name, breed, and age from this dog, and we've got these system.out.println statements inside of here. This has an unintended side effect because we're calling the system.out object by the println method. So what this does is this creates a dependency to the Windows console. All right, so I've maybe talked to some of you guys about this, I'm not sure, but when you put print statements inside of your class, and it's not like your driver or your demo program, right? You're putting it in the user-defined data type class, so you're putting it in like the player class or the scorecard class or something like that. What you've just done is you've limited that program to only being able to be used in a Windows environment where there's a console. So your class can no longer, exactly, Matthew, you make it dependent. It can no longer be used as an app on your phone. It can, or as part of an app on your phone. It can no longer be used as part of a website. It can no longer be used in a batch environment. It is limited to only being used in a Windows console environment as soon as you put those print statements in there. So it's an unintended side effect because you've limited the scope of your program. So where the print statements need to go is, what do I want to say? When we're creating these classes are user-defined data type classes. But then there's the actual program, which is your demo or your driver program that we've been using. That's where the print statements belong. Okay, so you've noticed like in the mini labs that we've been working on, you'll write your test case. You'll write your user-defined data type, which defines the assignment or the code generator, that sort of thing. But then we had you create a demo or a driver program, and that one was the one that interacted with the user, enter your score or enter your character, and then called your user-defined data type, creating an object, calling the different methods. But that driver or demo program is where your interaction with the user belongs, whether that demo or driver program works in a Windows console environment, or it's an app, or it's a website. That's where you're going to limit things down. Okay, so this is an unintended side effect. All right, that's all I've got to say about side effects. Do you guys got that? So intended side effects, unintended side effects, and no side effect if the instance variable is not modified. Okay. Algorithms. So just a couple of array algorithms. So there's the total, and I think we'll probably work on a high-low or something like that. So we have a couple of choices as to what we're going to do here if we need to compute a total and we have an array. Okay, so we can define an instance variable to contain the total. And then what we have to do is every method that would allow the array to be modified or would have some impact, whatever, on the array, we have to go in and make adjustments to that. So every time we add something to the array, we have to make sure we add to our total. Every time we update a value in the array, we have to make sure that we update our total. And every time we remove something from our array, we have to make sure we're deducting from our total. Okay, so we have to just investigate our whole class, and anywhere we make any change whatsoever to the array, we need to make sure that we're making a corresponding change to our total as well. So that's our choice number one. The second choice is to compute the total at the time that it's requested. So when somebody needs a total and they call the method to get the total, that it computes the method at that particular point in time. So which one, so these are two different choices. Which one do you think is better? Or maybe you think none is better. What do you guys think? I would probably lean towards the second one myself, compute the total at the time that it's needed. Now, the only exception that there might be to that is if you have just millions upon millions of records, right? So, and I think that's what you're getting at, right, Matthew, is, if you've got millions of records, then the time to compute that total could be astronomical. So, I would probably lean towards the second one, but if I have a ton of records I'm going to be processing, then I would go with choice number one. But choice number one is definitely lends itself to errors, right? Because you have to look at every single possible situation where the array could be modified. So this one is definitely simpler. But this one, in the case of a large amount of data, would be more efficient, but it's more challenging because you can't miss anything. All right, so here's an example of modifying everything. So on the add, we would have to say total equals total plus the value, and then add in this value, right? On an update, we have to subtract what's currently in the array, add in what's going to be in the array, and then set that position to the new value. And in a remove, we just have to subtract what's currently in the array and then set that position equal to null. So assuming these are the only three that modify the array, then these are the three adjustments that we would need to make. Versus with a total, we can do integer I equals 0, I is less than the array length, plus plus, total equals total plus array sub I. So again, I think it really depends upon the amount of data that you're trying to process, which one you choose. Very well could be. All right, high and low. So you guys just had a problem in your homework for last week with the high and low, right? So what you just do is you start out with your high and your low set to some initial value. So you can set them to the first element in the array, and that would be fine. So high and low are both set to the first element in the array, and then you process through the array one at a time, and then you check, is what at I less than low? Then that's my new low. Is it greater than my high? Then that's my new high. The important thing is not to put an else here unless you also check the if statement. So you can't just say, is it low, then it's my new low, else it's my high. You can't assume that just because it's not the lowest that it's automatically the highest. And vice versa is also true. You can't assume that just because it's not the highest, that automatically means it's the lowest. These are really two completely independent conditions. Okay, and so what I like to think of when you're working at a problem like this is, try to like visualize it. So maybe you're thinking about I've given you a stack of exams, right? And I want you to go through them, and I want you to figure out, as you're processing through these exams, what was the lowest grade that was earned on the exam and what was the highest grade that was earned on the exams, okay? That stack of exams is your array, okay? When you flip it over, the first one, that's when you're one iteration through the array, right? So you flip over the first one, and you say, well, is this, the very first time, that very first one is both your high and your low. So you've got a piece of scratch paper and you scratch out low equals whatever the score is, high equals whatever the score is. And then you set that piece of paper aside and then you flip over the next one. That's the next iteration through our array. And you compare, okay, this person earned a 78. Is that less than my low that I have on the paper? If it is, I scratch it out and write down my new value. And if it's not, then I check the high, is it greater than my high? And if it is, I scratch it out and put it on the paper, and then I shift it to the side. Then I grab the next sheet of paper and I do it again and again. So that big stack of papers you can think of as your array. Every time you flip one over, you're changing here and going on, and you're asking yourself, like, am I done yet? Am I done yet, right? So you're checking your condition, am I done? It's going through. When you visually compare the score of that exam against what you have written on your piece of paper, that's where you're doing your if statements here, checking. And when you're writing something on a piece of paper, that's when you're storing something into a variable here. You need to remember it, you need to keep track of it. So when you're thinking of these problems, try to visualize, what that might look like and try to think of, okay, I'm flipping papers, I'm doing the same process over and over again, that's going to be a loop, or, processing through my array and I'm comparing, just kind of think of those sorts of things. All right, searching through arrays. So there's a basic search algorithm. You start at the beginning, you work your way to the end, right? Integer I equals 0, I is less than the array length, I plus plus. If it equals the search value, I return the index position. Otherwise, if I get down here, I return -1. Again, it's only an if statement. If I find my search value, if it's equal, I'm going to return I. There's no else here. Okay, only an if. Because you can't assume that just because it isn't equal that the search value does not exist in the array, because you've only checked 1 at this point and then 2, and it could be that it exists further on. So only an if statement. Did I find it? Yes, return it, otherwise no, and if I get all the way to the end, then I didn't find it, and I'll return a -1 or false or something, whatever I need to return. Okay. There is also a binary search. So the first search starts at the front and works all the way to the end. So it's incredibly efficient if your value is at the beginning of the array, and not so efficient if your value is clear at the end of the array. Now, if you're only dealing with, 100 values or 10 values or something, it's not that big of a deal. Whereas if you're dealing with a couple million, then it really behooves you to be more efficient. So the binary search is going to be more efficient. Have you guys ever heard of like the binary tree? Does that ring any bells for you guys? So I know it was definitely back in the day with math and algebra and those sorts of things. So basically, a binary search is going to split everything in half. Okay, so we start left is our leftmost boundary 0, right is the array sublength, so that's our rightmost boundary, while left is less than right. So you start out, you have a 50 element array, you've got 0 and 50. 0 is definitely less than 50, so you'll move on. You figure out your midpoint, you add the two together. 0 plus 50 is 50, divided by 2 is 25. 25 is our midpoint. Close enough. Granted, there's 25 and 26 because we've got this even number, but we're going with 25 as our midpoint. And then we check the value. Now, this is assuming that the values are all sorted in descending order, okay? So we check the value at position 25. Is that less than our value? If it's less than our value, then we know that our value has to be in 26 through 50. Okay, if it's greater than our value, then we know our value's got to be somewhere in 0 to 25. And that's what we're doing here. If it's less than our value, then set our left equal to the mid plus 1. So our mid was 25. So 25 plus 1 is 26. We're leaving the right at 50. Okay. If it's greater than our value, then we're going to set the right equal to the mid and leave our left alone. So that would be 0 to 25. And if it's not less than, it's not greater, it's got to be equal, we found our value, so just return that midpoint. Okay, so you keep doing this process. If we've reset our lefts and right, then we check, is the left still less than the right? If it is, then we'll come in and we'll divide again. So let's say it was in the lower half, so now we have 0 to 25. We add those two together, divide it by 2, we get 12. So we'll check 12, is it less than our value? And we keep dividing and dividing and dividing until eventually we either find our value or we determine it doesn't exist in our data. So this will have us search half as many times as if we had to go all the way through the whole thing. So much more efficient. Okay. Search algorithms. So we've got the basics, start at the beginning, work your way out to the end. And then we have a binary search where we're splitting everything in half. All right. You guys good on those? What do you think? All right. We're going to move into big O. All right. Not my favorite subject, I'm just going to say, but a necessary evil, I suppose. So big O notation is a way to evaluate an algorithm for efficiency. Okay, so it's specifically used with array and array lists, and what you do is you count every, if you're analyzing an algorithm, you can count every single operation. And of course, some might be more labor intensive than others. Or you can count how often an array element is visited, assuming that each visit requires about the same amount of time. So, so what we're saying is if I look at element position 5, we're going to assume that if I'm accessing element position 5, that it takes about the same amount of time for me to access element position 10. Okay? All right. And we always go with the worst case. So if it took me 0.02 seconds the first time and in 0.01 seconds the second time, we're always going to assume 0.02. Okay, we haven't got to big O yet, but we're about to get there. Okay, so when you're doing big O notation, the first thing you do is you count the number of steps, you drop the constants, you look at the different inputs or different variables, and you drop non-dominant terms. Okay, so I'm going to go over an example here, but I do have a couple of videos here as well that you can, on the PowerPoint, that you can take a look at what they explain this. I hope I have my, no I don't. Okay, so with the big O notation, what they determined, I hope I'm not jumping ahead of myself. Let me click through a couple of these. Okay. So what they did is they ran a series of tests to look at efficiencies. And so they had some data and they put data, so they had this series of data. And so they ran some tests to look at which would be faster if they loaded the data on like a flash drive and they had a carrier pigeon take it from point A to point B versus if they sent something over the internet from point A to point B. So which do you think would be faster, the internet or the carrier pigeon? Okay, internet. Cool. All right, so what they found was that initially the internet was indeed faster. But as you increase the amount of data, like you kept adding more data and more data, it took longer and longer, as the data increased, the longer it took to send it via the net, right? But it took the carrier pigeon the exact same amount of time because it's all loaded on a flash drive. So it didn't matter to the carrier pigeon if it had 10 pieces of data or 10,000 pieces of data. It was still just carrying that one small flash drive, and the distance was exactly the same. And so with the data transfer via the net, it exponentially took longer and longer and longer versus with the carrier pigeon, it took the same amount of time. And so the carrier pigeon in big O notation would be a constant. Like it doesn't matter how much data you're sending across, it always takes the exact same amount of time. All right, so count the steps, drop constants, different variables, non-dominant terms. Okay, so let's see how this works. So selection sort, evaluating our selection sort. So n is the size of our array, okay? So we don't know how many values we have in there. It could be 10,000, it could be 10, whatever, but that's the size of our array. So to find the lowest value here, it's going to take n visits because we have to work from the front of the array clear through the end of the array. Okay, so this loop here, we're looking from 1 to the end, looking for the lowest value. So it's going to take us n tries. We're going to have to check every single element position looking for the n visit. All right. Then we're going to have 2 visits to swap the value because well, we're assuming the worst case, that the lowest value is in the very last element we're going to check. All right, so n visits to get all the way through. And then we're going to have 2 visits to the array to swap the value because we're going to take what's in the last position and swap it with one of the other ones, right? Then the next time through the array, we're going to have n minus 1 visits because we know that we've already sorted 1. So now we don't need to check that position anymore. So we're going to have n minus 1 visits to find the next one, but still 2 visits to swap, and so on. So if our array was if there were 5 elements in our array, we would have n plus 2 for the first time, then n minus 1 plus 2 for the second time, n minus 1 plus 2 for the third time, and then blah, 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 and so on, okay? And so it equals something like this. And so what you end up with is count the number of steps. So it's going to be, so it ends up with n times n plus n minus 1 times 2 is what we get. This is our n's. So counting the number of steps, it's n squared plus n minus 1 times 2. We're going to drop anything that's a constant. 2 is a constant. It's gone. So now we have n squared plus n minus 1. Different inputs equals different variables, but we only have one array. So essentially it means if we have multiple arrays, then we'd have different variables, but we don't. We just have one array, so that's n. And then we drop our non-dominant term. So n squared would be a greater value than n minus 1. So we drop this non-dominant term and we end up with n squared. So it's big O sub n squared. Okay, and this scales quadratically. Are you guys really, what are you guys thinking? Am I losing you all now? Big O notation? What do you think? It's very complicated. Oh, good. I'm glad you guys are here. Yay. Okay. So we've got this table. I just took this right from the book. These are different types of big O's. So this is a constant, O sub 1. This is constant. This is carrier pigeon. Okay. Logarithmic, linear. So this is going to do, you know, like you have your X and your Y axis and it's going straight up at a straight line. We have log, linear, we have quadratic, cubic, exponential, and factorial. All right. So here's how you're going to go about computing these things. So if it's O sub n, it's a linear, right? If it's O sub 1, it's constant, so it would be the same value every single time. If it's O sub n, and we have 100 pieces of data, and it takes us 5 seconds to traverse that data, then you're going to be linear, that straight line up the XY axis, right? So if we have 200 pieces of data, that's twice as much as 100, so that would be 5 times 2 is 10. So if it originally took us 5 seconds to process 100 pieces of data, it'll take us 10 seconds to process 200 pieces of data. 400 pieces of data is 4 times 100, so it's 4 times 5 is 20 seconds to process 400 pieces of data. All right, if you're in the quadratic, n squared, and we start out with 5 seconds to process, then what we're going to have is 100 to 200 is 2 times. So this will be 2 squared here times by 5. So 2 squared is 4. 4 times 5 is 20 seconds. So it's going to take 20 seconds to process 200 pieces of data if it took 5 seconds to process 100 pieces of data. And here we're at 400 pieces of data, so it's 4 times. So it's 4 squared times by 5. 4 squared is 16 times 5, so that gives us 80. So 5 seconds to process 100 pieces of data. It's going to take us 80 seconds to process 400 pieces of data. N is the number of visits. Yes. Or, yeah. Yep. Okay, and then cubed, it works the same way except for instead of squaring each one of these guys, we're cubing each one of these guys. There is a handy calculator out there for this, but you will not have access to that handy calculator on the exam. So you want to at least be familiar with how to calculate the different seconds. And there was something else, it seemed to me. Okay, so when I was looking at this, if there is, so here's how I figured out. Remember, you're going to do one variable for each array or array list that you're accessing. So in this case, we only have one array in the selection sort. We're dropping any constants, we're dropping any lower, like the less important variables, right? Because the steps were count the number of steps, drop the constants, different inputs equals different variables. So if there's different arrays, then you have different variables, and drop the non-dominant terms. So you're dropping constants, you're dropping non-dominant terms. You're going to have one variable for each array or array list and count the number of steps. So for me, here's how I got it down to quick and dirty. Because we're going to drop those constants and drop the non-dominant terms, right? And one variable for each array or array list. Well, we only have one array right here that we're processing, but we have 2 loops. Each loop, so this will be n squared. Because 2 loops, we're going to have to go through everything twice, so that's n squared. Okay? If I had 3 loops, that would be n cubed. If I only had 1 loop, then that's just n. All right, so that's kind of how I figure out which one of these, and I don't even know how to figure out how to do the logarithmic or the log linear. But the constant, no loop at all. Okay? So no loop at all, it's a constant. 1 loop, it's linear. 2 loops, it's quadratic. And these are nested loops that we're talking here. So if it's just one single loop, it's linear. If it's nested 2 loops, then it's squared. If it's nested 3 loops, a loop inside of a loop inside of a loop, then it's going to be cubic. And then your exponential comes up with more loops beyond that. All right, so that's kind of how I do a quick and dirty big O notation myself, because you're dropping everything else. And that brings us to the end. Thank goodness, huh? All right, so I was going to jump into the remainder of Lab 4. Oops, where am I at? Here we go. So we started Tuesday, I went over Lab 4 and talked about the test classes, right? So today I was going to focus on and we started a little bit on the class itself, but I was going to focus more on the bottom part of this. You cannot use T1s on the test. So the big thing is if you find the calculations getting challenging, then you're not doing them correctly. Because whatever calculation they give you on the test, you should be able to easily do by hand. So that was even true of the midterm. So what happened is when people got these weird, bizarre calculations on the midterm, they forgot about integer division or modulus. So the modulus was in there, but they were doing double division, or integer division was in there, and they were doing double division, which gave you bizarre decimal places and everything, where the values were like 5 and 2 or something like that was the result. So when you're doing your math, if you're sitting there going, I can't believe they expect us to do this math, step back and go, wait. Tina said that I should be able to do this by hand. How am I? Well, you can have scratch paper. So you can scratch things out on paper. You just cannot use a calculator to compute it. So think of your scratch paper as your whiteboard. All right, well, let's get into Lab 4. So I talked about the beginning, get holes played, get name, get score on hole. Okay, I think I might have talked about this one, but let's just start here. We've got 15 minutes. All right, so the first thing you need to do is you need to figure out, did the player even play this hole, right? Did they even play this hole? And I did not open up my my Java docs so we could take a look at this stuff. All right, so let me get back here now. We know how many holes have been played, right? Because we have an instance variable up here at the top that tells you how many holes have been played. So if somebody comes to you and says, I want you to tell me what the score is on the hole, then we want to check, is this hole number greater than or equal to 1, and is it less than or equal to the holes that have been played? Because it has to fall in a range of a hole that has actually been played. And if it is, then you're going to return the score that goes to hole number minus 1. And why are we doing hole number minus 1? Because it's an array, definitely. And if we take a look at that one Word doc here, it gave us an actual nice little picture up at the top. Score for hole 1 will be in 0, 2 will be in 1, and so on. So we need to subtract 1 to give us the corresponding element position in the array. Okay. Otherwise, we're returning invalid entry, our constant value that has like a negative 999. All right. So computing the total strokes on a hole, you need to do the exact same thing. You first need to check, is this through num, this through hole, is it even valid? Did we play this hole? Because if you didn't play the hole, then you're going to return invalid entry. But if you did play the hole, then you're going to need to go through and get the strokes on each hole. And those strokes are stored inside of your array. So you're going to start at position 0, and you're not going to do a less than or equal. You're going to do just less than through num because it's always 1 less, right? So you'll just add up. You'll do an accumulator, which is what we did, computing a total today in our PowerPoint. So you're going to just go through and add up those values. But first you got to check and make sure, is it actually a valid hole? Now, compute versus par is going to take a little bit more work. It's going to be exactly what you have up here, okay? But for each hole, you're going to have to get that hole. You're going to have to get the hole, so you're going to have to call the course to get hole, passing it the hole number, right? And then once you have the hole object, you're going to have to come out here and call the get par to get your par number. And remember, par is computed as par minus the strokes. Yep. No. Strokes minus par. I'm sorry, strokes minus par. Because if we had 5 on a 3, that would be 2 over. So strokes minus par. So what that's going to look like is, in here, you're going to have that hole, check and make sure it's a valid hole, and you've got a loop going on in here. And then you've got, say, your variable I is your loop variable, right? Then what you're going to have to do is you're going to have to do course.getHole, passing it I plus 1, right? Because 0, element position 0 is really hole number 1. And element position 1 is really hole number 2, and so on. Course, where am I at? Course, get hole, giving it the hole number, okay? Then once you've got, and this is going to be a hole object, so hole temp hole equals course.getHole, and it returns us a hole object. Now you can call the par, so par equals temp hole.getPar, okay? So now you can get the par, and then you've got your, whatever your total variable is that you've got going on, your total equals the total plus the strokes, which is at position I, minus par. Okay, so you're adding that to par. So you still have to check to make sure it's a valid hole at the beginning, and then if it is, you're going to loop through less than this through num, and each iteration through, you got to get the hole, get par, and then add your par value to your total strokes. Okay? Category. So we're counting the number of holes in a category. Count of holes in the category. And we have the category coming in. It's either going to be par under par, par, or over par, right? And you've got a constant that you're defining up at the top. So the first thing you need to figure out is this a valid category? Does it equal par, under par, par, or over par? If it doesn't equal one of those constants, if the value is not equal to one of those constants, then get out of there and return your invalid entry. Okay? If it does equal one of those constants, then you're going to loop through here, and they've given you the first one. So you're looping through, only looping through less than holes played. You don't want to process the empty positions in your scorecard. You only want to process the ones that actually have values, right? And all of your loops should have this in there, by the way. If the category is equal to under par and so you get your hole at I plus 1 and then you get par. If the score at position I is less than the par for that hole, then you're going to add 1 to your count. Okay? And so you're going to want to duplicate this for par, but in that case you're not looking for less than, you're looking for equal, right? And then you're going to duplicate the same thing for over par, and in that case you're not looking for less than or equal, you're looking for greater than. So you put all this stuff in just one loop here, and you don't need an else, you can just duplicate this just like this, and here you're just looking for over par, right? And then you're going to do it this way. Okay, and then you're going to look for par, and you're going to use an equal sign. Okay, so the first thing to do is check your category. Is it under par, over par, or par? Or is it not equal to those three things? Then return invalid entry. Okay, but if it is equal, then you're going to come down and process the rest of this stuff. Okay, this format item 1, these things most of it is done for you. Thank goodness. I always find this thing to be so confusing. Okay, so you are passed in an item and a width. So this is formatting individual values in the string. And this guy down here is actually formatting the whole string, and it calls that format item up there above. Okay, this is the max name length and then the item length here. So what our width is, we want in between each one. So the maximum length of the name, maybe we're only going to let 25 characters display on the scorecard, and we're only going to let each item have 5 spaces, kind of a thing. Okay. So we'll get in with our line, and we're formatting the name with the max length plus this open square. So let's get up. What's this supposed to look like? It's going to look like this. Okay, Sorum Stan with the square bracket, -2, you know, what he is relative to par. So this is what we're going to look like. Okay. So we format this, we call format item, passing it the name, our maximum length, and whatever gets returned, we're appending on that opening square bracket. So if we come up here, it passes in the name the first time, so Sorum Stan with whatever our length is that we're giving it. Let's say it's 15 characters. So we take a look at our item and we say, is our item greater than our maximum number of characters, 25, or whatever we've got going on here? If it is, then truncate it. Only return the item 0, space width. Okay, so truncate it. If it's too big, truncate. If it's not too big, then we need to pad it with spaces. Okay, so we're looking at our first position is the width divided by 2, and I guess we want to center it as well. Okay, so we're centering it, yeah, string to center. So we're centering it in there. So we're dividing our width by 2, and then we're dividing our item by 2 as well, so we can find out what the middle position for our item will be, and then we're centering it, padding spaces in the beginning and padding spaces in the end to center it. Okay, so this gets our name. We get versus par by calling our compute versus par. So if it's equal to 0, then we put an E here for even. Otherwise, if it's greater than 0, we just put a plus with the value of par. And if it's less than 0, we put a negative. Shouldn't it have a negative in there? Line plus format time. So we add on versus par down here. Prefix with plus. Prefix. Thought it had a negative in here. Wrong one. -2. I'll have to run through this because I think this bottom one should be, if it's equal to 0, if it's greater than 0, then in this case it should be negative, so it should have a -0 on it. But then they put the other thing on the end. So you need to add the code to display the scores for the holes. All right, and this one's giving you the total. Total strokes equals, get your total strokes. So then it's line equals line plus format item, integer.toString your strokes with your item length. Okay, so you're going to need to loop through the holes one at a time, okay? And you're passing it however many strokes were on that hole. So you're just calling your format line just like we did up above, right? And we're just appending this. So really you're going to have your loop going through, and you're just going to do line equals line plus format item, passing your integer.toString, your value at that array element position, comma space the item length. It says 4 spaces for each. So you're going to put an item length of 4. No, length of an item. So you've got the item length. So you're just going to pass item length there. And that will pass it out. So you're just going to loop through. If a hole has not been played, then it's just going to display 4 spaces for each is what it amounts to. And the toString is written for you, so you don't need to worry about anything down here. Well, it looks to me, if I look at the Word document, it should show either a positive or a negative. And so I can see if it's equal to par, they're displaying an E for even. If it's greater than par, I can see the plus. But what I don't see is the negative. But you know what? This will be a negative number. So this will, the versus par will actually be a negative number. So I don't think you're going to need to worry about putting a negative number in this particular situation because it'll already be negative. So you don't need to, it would end up with a double negative. So I think you guys are okay. All right. So don't, you know, this is like really looks confusing, but the reality is you're going to do a loop, right? And we got a whole bunch of loops up here already. Where is a loop? I know we have a loop somewhere. Right here. So we need to do the holes that are less than, where is my thing? So in here, don't let this like get you all confused. So you got your loop, and this gives us all the holes that have been played, but that's not, you're gonna have to have 2 loops. One loop that does a hole that's been played, or you can just do one loop that's less than the array length, but then you have to know at what point am I getting, is it not been played? Okay, so you could do array length here. Okay, so it's less than the array length, so you're processing everything. And then in here, you're just going to need to check to see, has this hole actually been played? So is if I is less than the holes played, then that means that we've actually played this hole, right? So in that case, you're just going to do this thing right here. But this, instead of taking this integer to toString versus par, the versus par value, you're going to do score sub I, right? And that's it. If it's not been played, else it hasn't been played, so then you're just going to say line equals line plus 4 spaces, right? Isn't that what it says? Add code to display 4 pages for each. Display blanks for holes not played. Add code to display 4 spaces for each. So you're just doing that. And really that's all it, and then the end of your loop. So don't try to make it more than it really is. You just take advantage of what you've already got. You're just plugging in this value right here. All right, well, we made it to 9:30 and we actually finished up lab 4. Do you guys have other questions on this? I know that formatting looks bad, but it's really not. Just kind of play with it with your demo program. You know what I mean? The driver program. Get the other stuff working first, and then you can just kind of play around with it. All right, any other questions? Keep your Java docs up so you can refer to the whole. Oh yeah, what do you have? I'll do my best. It's not my favorite. I can honestly say that log n. Well, if we go back and look at the binary search, go to slide. There's only one loop in a binary search, so it'll be O sub n. Oh, you don't think so? Maybe it is one of the log ones, because it's not technically looping all the way through. We're only going to loop halfway through. Yeah, the most you're going to do is visit half of them. So it probably is more efficient than log sub n. Yeah, if it's not sorted, the binary search won't work anyway. Big O for our binary search. They do T sub n minus 2 plus O sub 1. Yep, big O log sub 2. Yep, log sub 2n. Yep, you're right on there. So see, I'll let you. I can say that in 30 years of coding or 30 plus years of coding, no one has ever asked me to determine the big O notation of an algorithm, but that's not to say that it could not happen. I have definitely rewritten programs to be more efficient, but usually it's where I run them and I'm like, okay, this is taking way too long. How can I rewrite this to be more efficient? But yes, yeah, definitely knock on wood. Probably my next job will be like, what's the big O notation? Well, that's funny too. Well, and I don't know so much that that calculus is important for calculus is, I mean, calculus has its definite its importance, right? But I think it's more the logical approach that you take towards solving problems that helps you, especially in like computer programming, because it is very, very logical and there's definitely a way to approach things. And so I think where math comes into play is more in the approach that you take towards solving problems. Interestingly, when I actually got my degree way back in the day, computer science degrees really were not the norm. Like it was a very much of an up and coming type of a field. And so if you were studying computer science, it was actually more of a master's or a doctorate level type degree, not so much a bachelor's degree. So it was a relatively new thing to have a bachelor's degree in computer science. And so I did an internship at IBM. And what was interesting was all the people that were employed at IBM, they were math majors, music majors, and foreign language majors because they found that in studying those things that people had aptitudes for programming. So that was who IBM recruited at the time. Yeah, I think so too, Dylan. All right.